Welcome to the deep dive. You're probably someone who uses tools powered by large language models pretty much every single day.
Oh, yeah. Most people do at this point.
Right. And you already know the landscape, you follow the tech trends, and well, you've lived through this massive, sudden leap in artificial intelligence capabilities over the last few
It
years.
really was a sudden leap, wasn't it?
It was. But today, we're actually popping the hood. We're looking at a really fascinating stack of sources, specifically some highly technical architectural blueprints and research notes.
Yeah, these detail the exact framework that made this current era of AI possible.
Exactly, the transformer architecture. So our mission for this deep dive is to decode this dense framework. We want to look past all the hype and, understand the actual mechanics.
The why and the how.
Right. Why AI transitioned from this slow, agonizing sequential processing to models that are capable of absorbing and synthesizing just massive amounts of information instantaneously.
And to really appreciate the magnitude of that shift, I mean, we have to look at the landmark 2017 paper by Vaswani and colleagues.
Attention is all you need.
That's the one. This single architectural shift serves as the foundation for the models you interact with today. Everything from BERT to the entire GPT lineage.
It's all built on this.
Completely. Because before 2017, the field of natural language processing was sort of inching forward. It was constrained by its own infrastructure.
But after the transformer was introduced?
It practically sprinted. It was a complete re-engineering of how neural networks represent and process sequential data. It moved away from a pipeline approach to something entirely different.
Okay, let's unpack this. Because the breakthrough only really makes sense when you look at the bottleneck it actually solved.
Right.
We're talking about the predecessor to transformers, which are recurrent neural networks,
Right.
or RNNs.
Yes, RNNs. And the limitation there was this strictly sequential data dependency chain.
Meaning a model reading a paragraph had to process step 1 before it could move to step 2.
Exactly. And step 2 had to finish before step 3.
It's so tedious.
It is. That serialized execution was a massive critical path bottleneck. In computational terms, whenever a process requires a strict sequence, you're completely unable to exploit the parallel processing capabilities of modern hardware.
Because GPUs and TPUs are specifically designed to handle thousands of operations at the exact same time.
Right, but an RNN just forces them to sit idle. The latency per token, the time it takes to process each individual word, remains strictly linear with the length of the sequence.
So if you double the length of the text, you're doubling the processing time.
Exactly. Your throughput is capped by the architecture itself. Doesn't matter how much raw compute power you throw at it.
It's like a single file line at a grocery store.
That's a great way to look at it.
Like you can go ahead and build 20 new registers and hire 20 new cashiers, which I guess would be your data level parallelism.
Yes.
But if the store manager forces every single customer to go through one specific checkout lane, one after the other, you're still just stuck waiting.
You're entirely bottlenecked. And the genius of the transformer is how it shatters that single file line.
How does it actually do that?
Well, the blueprints describe the transformer solution as a massively concurrent fan-in, fan-out graph. It abandons recurrence entirely.
So no more sequential pipeline.
Right. Instead of passing information down a pipeline, it relies on a flattened, matrix-driven structure. By doing this, it aligns perfectly with the memory hierarchy of modern silicon.
It lets the GPUs actually do what they were built to do.
Exactly. It allows for massive parallel computation. Every token interacts with every other token in the sequence simultaneously.
Okay, but without that single file line, you've got a scenario where every single word is being processed at the exact same time.
Yes.
Which sounds like absolute chaos. I mean, unless there is a highly specific mechanism routing all that traffic, how does it figure out how the words actually relate to each other if it's not relying on the order they arrive in?
That routing mechanism is scaled dot product attention, or self-attention. It's a radically different approach to modeling dependencies.
Because it's not a chain anymore.
Right. Instead of relying on a sequential chain to pass context along, self-attention establishes direct global connections between all tokens at the exact same time.
And it uses 3 specific vectors to do this, right?
Yes. Queries, keys, and values. It functions a lot like a database retrieval system.
Break that down for us.
Sure. The query is essentially what a specific word is looking for in its surrounding context. The key is the descriptive label of what another word contains. And the value is the actual semantic content of that word.
So it's constantly matching queries to keys.
Exactly. The model computes pairwise relationships between every single query and every single key in the entire sequence. That's how it weighs the importance of each token relative to all the others.
And there is a detail in the research notes regarding the math behind those pairwise relationships that really stands out.
Oh, the scaling factor.
Yes, it's this specific scaling factor, 1 over the square root of the dimension of the keys.
I love this part.
It looks like this tiny minor footnote in the formula, but it actually serves as a crucial stabilizer for the entire architecture.
It really does. What's fascinating here is that without that specific dimensionality invariant stabilizer, the entire model would just collapse during training.
Really,
Mhm.
just from missing that one little fraction.
Yes, because when you take the dot products between these queries and keys in high-dimensional settings, you're essentially multiplying and summing large arrays of numbers to measure their similarity.
Okay.
As the dimensions grow, the resulting numbers can grow disproportionately large. And if those values get too big, they push the activation function, the softmax function, which turns these numbers into probabilities into regions where the curve is almost completely flat.
And when the curve is flat, the gradients are extremely small,
Exactly.
which means the learning signal just stops moving through the network.
It effectively kills the attention signal. It leads to vanishing gradients. The network's ability to adjust its weights and actually learn from its mistakes just stalls out entirely. So by scaling those dot products down by that specific square root factor, the architecture ensures that the attention weights remain differentiable and meaningful.
It decouples the width of the model from the training instability.
Precisely. That single mathematical decision is a huge part of why these models can scale up to billions of parameters without their training dynamics just falling apart.
If you think about how this plays out in the real world, like with machine translation, the impact is massive.
Oh, it changed everything.
Because early models relying on RNNs struggled terribly with long-range dependencies.
They just forget.
Right. If you were translating a long paragraph and a pronoun at the very end referenced a specific noun in the very first sentence, the sequential model had often forgotten the context. The information was diluted across so many sequential steps.
But with self-attention, the physical distance between words in the text no longer matters.
The model instantly connects the source and target words directly.
The attention weights provide a direct bridge. It shifts the entire paradigm from local sequential dependencies to global context-aware relationships.
So the model isn't just reading words anymore.
No, it's mapping a web of concepts. Every piece of data is aware of the entire surrounding landscape.
That brings up a really interesting structural problem, though. If you're listening to this, you know that language relies on syntax. Order matters.
Absolutely.
If the AI is absorbing all these words in parallel as this giant web of simultaneous connections, it loses the inherent timeline of the sentence.
It would just be a bag of words.
Right. Because the difference between the dog bit the man and the man bit the dog is purely sequential. The words are identical.
Very true.
Without a way to track order, that global web of context becomes completely meaningless. So how does it know?
The architecture solves this using positional encoding.
Positional encoding.
Since transformers don't have built-in sequential recurrence, they have to explicitly inject the position of each token into the data itself. And they have to do this before it even hits the attention layers.
How do they inject it?
They achieve this using additive sinusoidal functions, specifically sines and cosines of varying frequencies.
Okay, so it's essentially stamping a highly specific mathematical timestamp onto every single word before throwing it into the parallel processing mix.
That's a great analogy. It maps each token's position to a unique vector in a high-dimensional space. This acts as a spatiotemporal scaffold.
A scaffold?
Right. By using these periodic, overlapping sine and cosine waves, it creates a continuum. Tokens that are close to each other will have mathematically similar positional vectors.
And tokens further apart will have distinct recognizable encodings.
Exactly. This allows the model to learn relative positions in parallel with the semantic content. It completely decouples the preservation of order from the actual order of computation.
Now, the sources do point out a fascinating limitation to that spatiotemporal scaffold.
They do.
While a rigid linear sinusoidal encoding works wonderfully for text because the sentence has a clear, predictable, even narrative timeline, it struggles with systems where time is more fluid.
Because text is highly structured. But if you try to apply this basic sinusoidal encoding to chaotic or relativistic systems like audio synthesis or video processing, the architecture hits a wall.
Because time isn't always linear in those mediums.
Exactly. In audio data, time is not always perfectly linear. You can have temporal distortions where a sound dynamically stretches or accelerates or decelerates.
And a standard positional encoding can't handle that.
It tends to oversimplify those complexities. It essentially forces a rigid grid onto a fluid dynamic. So researchers are having to explore adaptive temporal kernels to handle irregular temporal patterns.
Because those basic sine and cosine waves just aren't flexible enough for the physical realities of real-world spatiotemporal dynamics.
Right. They need something that can warp and flex with the data.
Here's where it gets really interesting, though. We spent all this time talking about self-attention and positional encoding, but there's another core component of the architecture that the blueprints suggest is completely misunderstood by the mainstream.
Oh, you're talking about the feed-forward neural networks.
The FFNNs, yes. Mainstream discourse often brushes them off as simple, passive layers that just pass data along, but they're actually doing some heavy lifting.
They are absolutely the misunderstood heroes of the architecture.
Why is that?
Well, if the self-attention mechanism is responsible for resolving relational context, figuring out how words relate to one another globally across the sequence, the FFNN resolves contextual variation locally.
Okay.
It's a position-wise function approximator. That means it applies the exact same transformation to every single token individually, in parallel, after the attention layer has done its job.
Our sources describe the design of the FFNN as doing this massive asymmetric expansion and contraction.
Yes.
It takes the output from the attention layer, blows up the dimensionality, making it 4 to 8 times larger, runs it through an activation function called GLU, and then crushes it back down to its original size.
That expansion into a higher dimensional space is crucial. It allows the network to encode task-specific biases and explore complex feature interactions.
And the GLU function.
The Gaussian error linear unit. It's critical here. It warps those elevated vectors, probabilistically weighting the feature interactions based on their statistical significance.
So it's not just a flat threshold?
No, it's not just a simple threshold. It applies a smooth, nonlinear transformation that biases the network toward the most relevant dynamic interactions.
And then it crushes it back down.
Then the second linear layer collapses everything back down, effectively pruning away the redundant transformations.
Think about your family's chaotic group chat.
Oh boy.
You've got 5 different conversations happening at once, people talking over each other, random links being sent. That's kind of like the raw output of the attention layer.
Highly connected, but noisy.
Exactly. It's highly connected, but it can be incredibly noisy. It finds relationships, but not all of them matter.
Right.
The FFNN acts as a highly active filter for that noise. By expanding the data, using that GLU function to amplify what is actually salient, and then squashing it back down, it zeroes in on the exact message in that group chat that actually matters.
It filters out the noise.
It's an active anomaly resolver.
That's a perfect way to phrase it. It standardizes the representations generated by the attention layer. It ensures that the token-wise transformations don't drift away from the core relationships the model needs to understand.
And it does this independently for each token.
Right. And because it performs this filtering process for each token independently, it's perfectly suited for hardware optimized for parallel execution.
So we have this incredible attention mechanism building the global web, and we have these powerful FFNN filters cleaning up the noise. But the architecture doesn't just use one attention mechanism per layer, does it?
No, it doesn't. It uses something called multi-head attention.
Why multiple heads?
If we connect this to the bigger picture, using a single attention mechanism forces the model to compress all the relevant relationships into one single set of weights.
Meaning the syntax, the semantics, the deep context, the tone.
All of it. Trying to fit all that into one representation creates a massive representational bottleneck. Multi-head attention splits this process up into multiple parallel linear projections.
It splits it up.
It creates a manifold of distinct relational interpretations.
It's essentially giving the model multiple different brains to look at the exact same sentence simultaneously, with each brain caring about something totally different.
Exactly. One head might focus purely on grammatical structure, mapping the verbs to the nouns.
And another.
Another head might look strictly at long-range semantic associations, figuring out the underlying emotion or tone of the paragraph. Another might focus strictly on immediate contextual cues, like adjectives modifying the very next word.
And it constructs all these fields at the same time.
Simultaneously. And what's brilliant is that these specializations aren't hard-coded by the engineers. They emerge naturally through the training process.
There's also a huge structural benefit to this teamwork, graceful degradation.
Yes,
If you have a deep stack of transformer layers, an individual attention head might get noisy or fail to align properly with the data on a specific prompt.
it happens.
But because you have multiple heads working in parallel, the model can tolerate the failure of certain heads without a catastrophic loss of performance.
It aggregates the diverse perspectives. It ensures the output isn't hijacked by one flawed interpretation.
That redundancy is vital.
It is. And it ties into another structural safeguard heavily emphasized in the blueprints: residual connections.
Tell us about those.
When you're dealing with a modern transformer model that scales to hundreds of layers deep, you run into a physical limitation of deep learning. As data passes through layer after layer of nonlinear activations and linear transformations, there's a very high risk of the gradients degrading.
The signals the model uses to learn.
Right. They can degrade or vanish entirely by the time they propagate backward through the network.
So residual connections act like bypass lanes on a highway.
Perfect analogy.
Instead of forcing the data to travel through every single mathematical choke point, they take the input of a layer and add it directly to the output of that same layer.
It gives the data a fast pass.
So the learning signal doesn't get lost in the math.
Exactly. It creates direct pathways for gradients to propagate. This prevents the high-dimensional optimization landscape from spiraling out of control.
Because without these bypass lanes, what happens?
The math gets messy. The weight matrices can unpredictably amplify or dampen the signals, and the model simply loses its ability to learn. By smoothing the loss surface, residual connections stabilize the entire training dynamic.
So they're essential for scaling.
Completely. Scaling these models to the size of something like GPT-3 or GPT-4 would be virtually impossible without them. The network would suffer from catastrophic forgetting and just stall out during training.
So what does this all mean? We've talked about all these incredible innovations, breaking the sequential chain, connecting everything at once, filtering out noise with FFNNs, using multiple heads for diverse context, and stabilizing the training with residual connections.
It's a lot of power.
It is, but there is a massive catch to all of this unprecedented parallel power.
There always is. The catch is a severe operational bottleneck. It's an O of n squared, or quadratic memory complexity.
As n squared.
Yes, because every single token must attend to every other token in the sequence to build that fully connected global graph. The mathematical operations don't just scale up linearly as the text gets longer.
They explode.
They explode exponentially. Storing and calculating all those attention maps requires an immense, almost unbelievable memory footprint.
It's a trade-off.
A fundamental trade-off. You get unprecedented dependency density, but you pay for it in memory and compute.
The statistics in the research notes really put this into perspective.
They're staggering.
Just training a basic, standard-sized BERT model from a few years ago can require 10 to the 15th power FLOPS.
Floating point operations per second.
Right. For a single full epoch of training. We are talking about data centers drawing enough electricity to power small cities.
Server racks generating massive amounts of heat.
And modern CPUs or GPUs spiking to 90% utilization instantly just to handle the matrix multiplications.
And that quadratic burden doesn't magically disappear once the model is trained.
It doesn't.
No, it persists during inference, which is the actual generation phase when the model is answering a prompt. Every single forward pass requires substantial compute.
Because it's still calculating the global web.
Exactly. If you double the length of the input sequence, the memory requirement quadruples. This is why scaling transformers to handle very long book-length sequences is the single biggest architectural challenge in the field right now.
For you listening, this exact quadratic memory bottleneck is the real-world reason why your favorite AI chatbots have token limits or context windows.
That's right.
It's the underlying reason why you can't just copy and paste an entire 10,000-page encyclopedia into the prompt box and ask the AI to summarize it all at once.
The hardware would physically run out of memory trying to calculate every single word's relationship to every other word simultaneously.
The math just becomes too large for the silicon to hold.
It does. Now, the field is actively researching efficient attention variants to reduce this overhead.
Like what?
They're looking into sparse attention, where tokens only attend to a limited subset of other tokens, or linear attention approximations.
But those have trade-offs too, right?
Always. It might save memory, but you introduce accuracy degradation or latency issues in distributed networks. You lose some of that rich global context that made the transformer so revolutionary in the first place.
Let's bring this all together. We have journeyed through the architecture that completely changed the landscape of modern technology.
We covered a lot of ground.
We did. We've seen how transformers dismantled the slow, single-file bottleneck of recurrent neural networks. By utilizing self-attention, they map out the entire context of a sequence simultaneously, breaking the barrier of physical distance in text.
And by injecting positional encoding, they maintain a rigid spatiotemporal scaffold to keep track of order.
Exactly. They use feed-forward networks as active filters to amplify the most crucial anomalies, and they rely on multi-head attention and residual connections to ensure the entire massive system remains stable, diverse, and capable of scaling to hundreds of billions of parameters.
It's a beautifully complex web of parallel processing.
This raises an important question, though. If that quadratic memory bottleneck is the ultimate threat to scaling AI further, how do the engineers push past it?
The source material leaves us with a truly fascinating look at the future of this architecture. Researchers are exploring concepts that move beyond static matrices,
Moving into what kind of ideas?
diving into ideas like adaptive head pruning and dynamic attention routing.
Meaning the AI would actively alter its own structural footprint while it processes a prompt.
Exactly. Imagine an architecture that can dynamically dismantle its own brain on the fly.
That's wild.
During inference, if the AI evaluates a specific prompt and realizes that certain attention heads or specific relational pathways are redundant for that particular task, it actively drops them.
Just turns them off.
It temporarily turns off parts of its own network to save power and memory. And it does this without losing the richness of its contextual understanding.
It balances expressiveness with efficiency in real time.
It continually adapts its size to the complexity of the input.
An AI that learns to dynamically prune its own architecture just to survive its own massive resource demands. That is something to mull over the next time you're typing a prompt into a chat window and waiting for that instantaneous response.
It really is.
What will the next evolution of this technology look like when the AI starts optimizing its own structural footprint? We want to thank you for joining us on this deep dive into the transformer architecture. Keep questioning how the tools around you actually work, and we will catch you on the next one.